In this module of Chapter 1, Module 1.5, I covered Gini coefficients and Lorenz curves, as well as cohort concepts and rates, ratios, and proportions. The Gini coefficient was originally developed to show the income distribution among residents of a population. For example, 10% of a population possess 90% of the wealth. But it can also be used to represent the degree of inequality in the distribution of any quantitative variable among a group of individuals. The Gini coefficient is based on the Lorenz curve, which plots the proportion of the total of a given metric, for example, income or offspring, possessed by the bottom X% of the population. The 45-degree line represents the perfect equality of this metric, e.g. 25%, 50%, and 75% of females produce 25, 50, and 75% of the offspring, respectively. However, more typically, we find something like 25% of the females produce 50% of all offspring, or as before, 10% of people possess 90% of the wealth. The Gini index is computed from the equation A divided by A plus B, where the numerator is the area between the 45-degree line of equality in the Lorenz curve, and the denominator is the total area under the line of equality. This figure shows the Lorenz curve for the distribution of egg production in 1,000 Drosophila females. The area occupied by A in this figure is 0.139. Because the area of the right triangle, that is the total of the both shaded zones, in this figure is 0.5, the Gini coefficient for this Lorenz curve is computed as 0.139 divided by 0.5, or 0.278, indicating a moderate skew of reproduction among these females. The strength of the Gini coefficient includes, first, it's simple to compute and easy to interpret. It's used to compare patterns of inequality across groups, and it serves as a comparative index for historical trends or treatment comparisons. Cohort concepts. Multiple cohorts can be followed either cross-sectionally, where demographic data is collected by observing subjects across all or a subset of cohorts at the same time, or longitudinally, where demographic data is collected by observing the same subjects over time. The main advantage of a cross-sectional study is that the information can be collected on all age groups over a short period. The disadvantage is that it confounds age differences with cohort or period effects. The main advantage of longitudinal studies is that the data track long-term trends as cohorts and individuals age. The main disadvantage is that longitudinal studies require much more time and typically many more resources. Rates, ratios, and proportions. Quantities in demography can be expressed as a ratio, which compares frequencies of two mutually exclusive quantities. As a proportion, a special type of ratio in which the numerator is part of the denominator. For example, P equal A over A plus B. And a rate is a measure of change in quantity, that is a number, per unit of another quantity, typically time, on which the first quantity depends. Rates are usually associated with dynamics of populations or cohorts, such as growth. Ratios and proportions are often associated with population statics, such as sex ratio or age structure. Crude rates. This uses total population in the denominator. For example, crude birth rate is births per number in the population. Crude death rate would be deaths per number in the population. A crude rate of natural increase would be the difference between crude birth and crude death rates. They are called crude in that they consider all individuals regardless of age or sex. Age-specific rates. These are the same as crude rates, except with age restrictions for both the numerator and the denominator. For example, age-specific rate for fecundity for an individual age 20 counts only offspring produced by females in that age group, and counts only females of that age in the denominator. Restricted rates. These apply to any special subgroup. For example, in human demography, births to married women is termed marital age-specific fertility rate. Rates by topic. These rates apply to each specialized topic in demography. For example, total, gross, and net rates for topics ranging from mating and fertility to marriage and migration. Intrinsic rates. These are rates that prevail in a stable population. These are referred to as intrinsic rates in that they cannot reflect any accidental or transient short-term feature of the age distribution. In other words, they are considered intrinsic or true rates. I will cover this in more detail when we get to Chapter 5 on stable population theory. This completes the last module of this first chapter of biodemography.